After a detailed discussion of inertia, tensor and angular momentum of a rigid body, today we are going to see the calculation or finding the expression for rotational kinetic energy of a rigid body. Actually, you will see that the expression for rotational kinetic energy of a rigid body can be obtained in terms of the inertia tensor and the angular momentum vector. So, this is a very important concept and very important for your examination purpose. But the concept is very simple. If you have watched my previous video, this session will be very easier to you. Okay? As we have to find the rotational kinetic energy of a body, it means you have to consider a rigid body which must be rotated about some axis, passing through a fixed point in the body. So I have shown in this figure, here you can see that this is a rigid body, okay? And this rigid body is rotating about an axis which passes through a fixed point O, which is located inside the body. And I have also assumed that along this axis of rotation, the unit normal is n hat, or the unit vector directed in the direction of axis of rotation is n hat. So definitely the angular velocity omega with which the body will be rotated about this axis, that will be directed in the direction of this n hat. Okay. Now, how we can find the kinetic energy of this body? The process is straightforward. As you have calculated the angular momentum, in the same line you can think. As we consider that a rigid body is just a combination of a large number of rigid particles. Okay. So, assuming a large number of particles compose this rigid body, we can find the kinetic energy of one of the particle under consideration, and after summing the values of kinetic energy for all particles, you can get the expression for kinetic energy of this rigid body. And so you can see in this figure, I have considered an ith particle here located at point P, whose position vector I have shown with respect to the fixed point O is Ri. And we will also consider that this Vi is the linear velocity of this particle. Okay? And since we have assumed that the rigid body is rotating with angular velocity omega, and you know, angular velocity of a rigid body does not depend on the particle. It means the angular velocity of each and every particle of the body is same. So if you are talking about the ith particle, then I would like to ask you, what will be the angular velocity of this ith particle? Answer will be omega. I will ask you, what is the angular velocity of jth particle? Answer will be omega. Okay. And you know how this omega and this V is related. V, you know, is equal to omega cross R. Here we are talking about ith particle whose position vector is Ri. So you can write that Vi is equal to omega cross Ri. Okay. Now, for finding the kinetic energy of this whole body or entire body, first of all, we will define the kinetic energy of this ith particle, and after summing that value of kinetic energy for the entire number of particles, you will get the kinetic energy of entire rigid body. So let us see, as I have written here, that this Vi is equal to omega cross Ri, as I have told you, and the kinetic energy of the ith particle, okay, which I have denoted by the symbol Ti, that is given by 1/2 mi vi square. This is the usual expression for kinetic energy as you study it in your course on elementary mechanics. Okay. Now, since Vi is a vector and you know a square of a vector is what? That is simply the scalar product of the vector with itself. So instead of Vi square, you may write Vi dot Vi. Okay? Now, as I have told you, now if your aim is to find the total kinetic energy of the body or the entire body, then what you will do? We will simply take the summation where summation will extend to all particles of the body. Okay? So the kinetic energy of the body denoted by the symbol T is given as summation over I, where I will run from 1 to n, where n is the total number of particles. And that is given by summation over I half mi Vi dot Vi. But as you know, Vi is equal to this much, omega cross Ri. So instead of one of the Vi, let us substitute omega cross Ri. So I have written here omega cross Ri at the place of one of the Vi's. Okay. Now, you know a very important property of a scalar triple product, that A dot B cross C is equal to B dot C cross A. This is actually the property of interchangeability of dot and cross in a scalar triple product. Okay, you can actually interchange the dot and cross. Okay, but the product will remain same. So instead of Vi dot omega cross Ri, you may write omega dot Ri cross Vi. Okay. Now, since omega is independent of the particle, it is same for all particles. So this summation is not implied for omega, and therefore you can take this omega outside of the sign of summation. So I have written here, you can see this is 1 over omega dot, because here there is omega dot. Okay, and summation over I Ri cross Mi Vi. Since Mi is a scalar, so you can associate this scalar with any of the vector Ri or Vi. I have associated it here with Vi. But what is Mi Vi? You know, this is the linear momentum of the ith particle. And from the definition of angular momentum, you know that R cross P, that is R cross MV, is the measure of angular momentum of a body. Okay, so here Ri cross Mi Vi, this will be the angular momentum of the ith particle. But when you sum up it, that will give you the total angular momentum of the rigid body about that very axis of rotation. And we will write instead of this factor L, which is angular momentum of the rigid body. So we know L is equal to this much. You have studied it in your previous lecture, and this is summation over I Ri cross Mi Vi. Okay, about the fixed axis, about the fixed point O. Okay, and therefore the expression for kinetic energy T, now you can write in this way: T equal to half omega dot L. This is the basic expression for kinetic energy of a rotating body. You can say that this is rotational kinetic energy because you have considered that our body is rotating about an axis passing through a fixed point inside the body. Okay, so this is the basic expression, and I will tell you, you must remember this expression as you remember T equal to half mv square. Just like that, you must now remember in this level that in general the rotational kinetic energy of a rigid body is given as T equal to 1 over 2 omega dot L. Okay, you know omega dot L is a scalar, half is already a scalar, this is just a number. So this kinetic energy is a scalar, and this a scalar product can be defined easily, because you know omega is given as omega xi plus omega yj plus omega zk, and L is given as Lxi plus Lyj plus Lzk. So omega dot L, you know, omega is given as omega xi plus omega yj plus omega zk, okay, and dot L is Lxi plus Lyj and plus Lzk, you know. And in accordance with the definition of a scalar product, you know, this will be simply equal to omega x Lx plus omega y Ly plus omega z Lz. Okay. Now remember what we have learned in your previous video. You have actually studied the angular moment components of angular momentum vector in terms of inertia tensor, moment of inertia and product of inertia. You have seen in my previous video that this Lx, which is the x component of the angular momentum vector. When you say x component, that is actually the body x-axis. And relative to the body x-axis, you have already learned that Lx is given as Ixx omega x plus Ixy omega y plus Ixz omega z. Okay? You have learned in the previous lecture. Okay? And this Ly, this is given as Iy omega x plus Iyy omega y plus Iyz omega z. And this Lz is given like this, you know. So I have substituted the values for Lx, Ly and Lz, which we have already learned in our previous lecture. Okay. Now let us simplify the RHS of this equation a little bit. You can see that the first term in this, this is Ixx omega x times omega x. This will be half has been taken as a common factor. You can see this is Ixx omega x square. Then take the first term from here. This is Iyy times omega y square. Now take this. This is Izz omega z square. Okay. Now take the terms of product of inertia. You can see you have learnt in previous lecture that inertia tensor is a symmetric tensor, and Ixy is same as that of Iyx. Similarly, Ixz and Izx both are equal. Iyz and Izzy, these are also equal. So now see, here this term is Ixy times omega x omega y, okay? And also here, sorry, here this was Iyy term. I have wrongly said that this. This is Iyx times omega x omega y, but Iyx is equal to Ixy. So this will be 2Ixy omega x omega y. Similarly, now see this third term. Ixz omega z times omega x, and here 2, this is Izx, which is equal to Ixz, okay, omega x omega z. So this will be again 2Ixz omega x omega z. Similarly, this term Iyz times omega y omega z and Izzy times omega y omega z both are equal. So this is 2yz times omega y omega z. Okay. And therefore, the expression for kinetic energy can be written as 1 over 2 Ixx omega x square plus Iyy omega y square plus Izz omega z square. And when you will multiply by this factor 1 over 2 to the last three terms, the 2 will cancel out and so the remaining three terms are Ixy omega x omega y, Ixz omega x omega z, Iyz omega y omega z. Okay, so this is the another expression for rotational kinetic energy of this rigid body in terms of the moment of inertia and the product of inertia. Here Ixx, Iyy, Izz, you know, these are the moment of inertia of the body about the respective three axes, while Ixy, Ixz and Iyz, these represent the product of inertia with respective planes. Okay, so this is another important equation. Okay, now this equation which we have obtained here in equation number A2 can be written in a compact form. Okay, in compact form you may write this equation like this: T equal to 1 over 2 summation alpha beta from 1 to 3 I alpha beta times omega alpha times omega beta. Actually here I have taken the numerical values for alpha and beta, but that numerical values only stands for x, y and z. X, y and z. For convenience I have taken this in the form of numerical value, as you can take this x as 1, okay, y as 2, z as 3. Okay, so this will be I11, I22, I33. This will be I12, this is I13, this is I23. Okay, so in the similar manner, when you will substitute the values of alpha and beta and sum up, you will get that equation. So that equation may be written in compact form like this. You can check it. Okay. Now, till now we have taken the moment of inertia and product of inertia with respect to a body set of coordinate axes. But you have learnt about the principal axis transformation in my previous video. And you have seen with respect to the principal axis, product of inertia vanish. Product of inertia vanish. Only the diagonal elements of the inertia tensor remains non-zero, which are called principal moment of inertia. And we have denoted that principal moment of inertia by the symbol I1, I2 and I3. Okay? So in that condition, these last three terms will vanish. Okay? And only the first three terms will remain in the expression for t, and at the place of Ixx, then you have to write I1, at the place of Iyy, you have to write I2, and at the place of Izz, you have to write I3. You can understand this thing in another way. You have learnt in the previous lecture that when you talk about the angular momentum and the inertia tensor with respect to the principal axis of the body, then the angular momentum vector L is given like this. This is I1 omega xi plus I2 omega yj plus I3 omega zk. Or instead of omega x, omega y, omega z, you may write omega 1, omega 2 and omega 3. Okay, so in this condition, L has only three components. Here, L has actually, sorry, not L, but here L has three components, but here inertia tensor does not behave like a tensor, but that behave like a scalar. Okay. And these are I1, I2 and I3, you know, are the principal values of inertia tensor. Okay. So in this condition, when we talk about the principal axis of the body, then what will be the expression for kinetic energy of this rigid body? So let us now start again with the basic result which we have obtained for the kinetic energy in this equation A1. So now T will be given by half omega dot L, but you know omega is equal to this much. This is omega xi plus omega yj plus omega zk, and L you have seen here. In this case, L is equal to this much. This is I1 omega xi plus I2 omega yj plus I3 omega zk. Okay? And when you will take the scalar product, which is very easy, you can see T comes out 1 over 2 I1 omega x square plus I2 omega y square plus I3 omega z square. Okay? I3 omega z square. You can also write this expression in this way. Instead of omega x, you can write omega 1. Instead of omega y, you may write omega 2. And for omega z, you may write omega 3. So this is the expression for kinetic energy of the rigid body in terms of the principal moment of inertia. Okay? Principal moment of inertia. So, or you can say that this expression involves the principal moment of inertia. Okay? Again, this equation A3, which represents the expression for kinetic energy in terms of principal moment of inertia, can be written in a compact form like this. You can write T equal to 1 over 2 summation sorry, here there will be no beta. I have wrongly written here beta. You should write only alpha. Okay? This is alpha 1, 2, 3. Alpha 1, 2, 3. And this is I alpha omega alpha. You can check. When alpha will be taken 1, you will have this first term. When alpha will be taken 2, you will have this second term. When alpha is 3, you will have this third term. So this equation A3 may be written in compact form by this expression. Okay? So now we have obtained the expression for kinetic energy of a rigid body rotating about an axis in two forms. First of all, you have obtained the basic equation, then you have obtained the then you have transformed that very equation in terms of inertia tensor. Okay? And after considering the principal axis, the kinetic energy expression becomes like this. Now actually, you have studied in your lower classes when you study moment of inertia and rotational dynamics in +2 level. Then you have definitely seen your textbook that the expression for rotational kinetic energy is written in the book like this. This is half I omega square. And your teacher says that this I is the moment of inertia of the body about the axis of rotation and omega is its angular velocity. It is also correct. But till now, the expression for kinetic energy, what we have obtained, that is not exactly in this form. T equal to half I omega square in this form. Our results are not here. But surprisingly, you will see that actually we can express the expression for kinetic energy in this usual form, which you study in your course in elementary mechanics. Okay? So how you can say that we can express the rotational kinetic energy in this simple form T equal to half I omega square? Now let us see. Let us try to understand it. Okay? So I have written that in elementary mechanics, rotational kinetic energy is given as T equal to half I omega square. Definitely in your +2 level, intermediate of science level, you have studied it. And your teacher has definitely told you that this is the expression for rotational kinetic energy. Okay? But how we can transform our previous result into this form? Let us now see. Actually here, you know, I is the moment of inertia of the body about the axis of rotation. Okay? But in this rigorous calculation, we may express the kinetic energy of the body in the above form. But how we can express? Now let us see. And for this, you have to start from again the basic equation for kinetic energy, which we have learned that T is equal to half omega dot L. Omega dot L. But how L has been defined, how L is defined, you have already learned in my previous video. I am just repeating the thing. If you may permit, I can write directly the expression for L which we have obtained in my previous video. But for your clarity, so that you have no confusion, I am again repeating the things. You can see, basically L, which represents the angular momentum of the rigid body, that is defined as summation over I, Ri cross Mi Vi. Okay? And again, you know, Vi is replaced by omega cross Ri. Okay? So I have replaced it. Let us see quickly. Now, this is just the triple vector product, Ri cross omega cross Ri. This is triple vector product. And you know, from the definition of triple vector product, this can be written as Ri dot Ri times omega minus Ri dot omega times Ri. You can write. You have also learned in previous lecture. Okay. Now, this expression may be written as summation over I, Mi. Okay. Ri square, you know, Ri dot Ri, this is written as Ri square. And here I have taken Ri times Ri dot, mark it, here there is dot ahead of this Ri. And omega has been written here. This is just a rearrangement of the terms. Okay. Now, instead of the operator, mark it, the expression inside this curly bracket, see this expression. Can you say that it is a physical quantity or it is a mathematical operator? Certainly you must say that this is a mathematical operator due to the presence of this dot. Okay? This is a mathematical operator, not a physical quantity. So you can say that when this operator inside the curly bracket is operated on this angular velocity omega, the result is the angular momentum of the body. Okay? And we denote this operator by the symbol L, small l or little l. Okay? So you can now write in terms of this operator L, which has been written instead of the expression inside this curly bracket. You can write the expression for T in this way. This will be half omega dot L. But this capital L, which is angular momentum, is now equal to little l omega, where little l is an operator. So this is T equal to half omega dot L omega. Okay? But how we can simplify it? For this, you have seen in the figure that we have considered that the unit normal vector along the axis of rotation is n hat. And you know, angular velocity is an axial vector. It will be directed in the direction of this n hat. So omega is directed in the direction of n hat, and so we can write omega equal to omega n hat. Okay? So now, instead of omega in this equation A5, we will write omega times n hat. So T is equal to 1 over 2 omega n hat dot L omega n hat. Okay? Now, this expression can be written as omega square over 2 times n hat dot L n hat. But what is this L n dot L n hat? You will see that actually this quantity is the moment of inertia of the body about the axis of rotation. But how you can say that this quantity is I, which represents the moment of inertia of the body about the axis of rotation? Now you can see, I am giving you a very simple proof that this n dot L n hat, that is equal to I, which is the moment of inertia of the body. You can see. So I have simplified this n hat dot L n hat. Okay. You know, this operator L has been written instead of this. This is the expression for this operator. Okay. So you can see n dot L. For L, I have written the expression inside this curly bracket, and here n hat is at each. Okay. Now let us simplify it. This n hat is at each, you can see n hat dot and summation over mi. Now take the multiplication of the factor inside this curly bracket with this n hat. So the first term will be Ri squared times n hat minus Ri times Ri dot n hat, because here there a dot is present. Okay. Now again take the scalar product of the expression. Now this is not a operator inside the curly bracket. Now it is a physical quantity. Okay. And we will take its scalar product with this n hat. As you know, in case of a scalar product, commutative law is followed. A dot B is equal to B dot A. Okay. So you can write that this is summation over I mi Ri square n hat dot n hat. I have taken the scalar product with this n hat. Okay. And now here Ri dot n hat, this is a scalar. This is a scalar. So n dot will be operated on this vector Ri, because n hat is a vector. So the second term is Ri dot n hat times Ri dot n hat. Okay, it is a simple calculation. And this is summation over I mi times. Now you know n hat is a unit vector. And as it is a unit vector, so n hat dot n hat will be what? That will be 1, just like I dot I is 1, j dot j is 1, k dot k is 1. Okay. So this is simply Ri square, which has been written as Ri dot Ri. Instead of Ri square, I have written Ri dot Ri. Okay. And this second term has been taken at each. Okay. Now let us take this Ri dot as a common factor. You can take it. So you can write this expression as summation over I mi Ri dot Ri minus n times Ri dot n hat. Okay, it's very simple. Now this expression Ri minus n hat times Ri dot n, this expression can be written as n hat cross Ri cross n hat. This is a scalar triple product. But how? Let us check. I hope you have you know the definition of a scalar triple product. N hat dot Ri cross n hat. What is this? According to definition of a scalar vector triple product, you know this is n dot n times Ri minus Ri dot n times n hat. But n hat dot n hat, that is 1. So this is simply Ri. Okay, and minus n hat times Ri dot n hat. So you can see that instead of this factor, you may write n hat cross Ri cross n hat. Okay, I think you have clearly understood. Now, by virtue of the property of a scalar triple product, this vector triple product n hat cross Ri cross n hat can be written as this. This is just a simple property of the scalar triple product, which you have learned in your course on vector algebra. Okay, and so instead of this vector triple product, by the use of the property of a scalar triple product, I have written this as Ri cross n hat dot Ri cross n hat. Okay, I have written it. And now along with this Ri dot this much, this is equal to this one. Ri dot, sorry, I have told earlier wrongly. Ri dot n hat cross this much. This is written as Ri cross n hat dot Ri cross n hat. Okay. So now you can see A cross A, sorry, A dot A, that is simply a square of modulus of A. Similarly, Ri cross n hat dot Ri cross n hat. What is that? That is mod of Ri cross n hat. Okay. But what is this mod of Ri cross n hat? And for this you can see your figure which I have drawn in our first page. So let us see what is this Ri cross n. For this let us draw a perpendicular from point P, that is the position of ith particle on this axis of rotation. Okay, and let us consider that this angle is theta I, which this position vector makes with n hat. So when you will define Ri across Ni, Ri cross Ni, a modulus, what will be this? This will be mod of Ri, okay, times mod of Ni, okay, times sine theta 1, okay. But modulus of not Ni, but modulus of n hat, not I, okay. This is 1. So this is simply Ri times sine theta 1. But from the geometry of figure, you can see that this sine theta 1 is equal to what? This is Ri times PQ divided by Ri, modulus of Ri. So this will cancel out. So mod of Ri cross n hat, not Ni but n hat, this is simply equal to PQ. And what is this PQ? PQ is the perpendicular distance of this ith particle from the axis of rotation. That is perpendicular distance. So you can see I have written that this is actually the perpendicular distance of the ith particle. Mod of Ri cross n hat, this is Ri sin theta, this is equal to PQ. And this is perpendicular distance of the ith particle from the axis of rotation. Okay. And you have definitely the basic knowledge of moment of inertia. You know, if you define the moment of inertia of a particle with respect to some axis, what you do? You define it like product of mass of the particle and the square of the perpendicular distance of the particle from the axis of rotation. So what is this? This mi times this much square, this is actually the moment of inertia of ith particle with respect to the axis of rotation. And when you sum up it, when you take this summation, then you will get the moment of inertia of the body about the axis of rotation. Okay. So this n hat dot L times n hat, which is equal to this much, this is equal to the moment of inertia I of the body about the axis of rotation. Okay. So now what is this n dot L n hat? We have already recognized. Now let us substitute this value of n dot L n hat in this equation A6. You can write I instead of this, and therefore the expression for kinetic energy of the body is given as 1 over 2 I omega square. And this is the usual expression which we have learnt in your elementary course of mechanics in your lower classes. Okay. So I think now how we can derive the expression for rotational kinetic energy of a rigid body have become very clear to you. Okay, thank you very much.